Hi, I'm Tara Madhyastha, and I'm going to talk to you today about neuroimaging workflows in the cloud. As a disclaimer, I work for Ronin, which is a company that develops and licenses a research computing platform that runs on AWS. However, neither Ronin nor AWS have had any input into the content of this presentation. Everything I say is my own thoughts and opinions. Now, I'm going to begin by talking about how we do neuroimaging the traditional way, and this reflects what I experienced in my research lab before I joined AWS. One of the things you could do was buy a big server, or if you were lucky, you could get hold of some time on the cluster. You would store data wherever you could, and you would try to use scripts, workflow, and maybe even containers to manage reproducibility. Now, the question that I want to pose here is, do these approaches scale? And moreover, do they scale to the cloud? Because things are a little bit different there. We know that when we use neuroimaging for large-scale studies, we need to scale. And by that, we need more compute power to manage all the subject analyses. We need more space for the data itself that we collect and the results. Because many large-scale studies are necessarily multi-site, we need to be able to share the data across multiple sites, have pretty complex permission structures, and we need to be able to allow collaborators and partners to get to that data. Because nobody wants to come to the end of a $10,000 analysis and question, did we set flag X in step 5 correctly? We want to make sure that we script our analyses and do so in such a way that we can reproduce the results without question. All of this requires quite an investment in understanding infrastructure, but scientists don't have time to be scientists and also to become certified cloud architects. So the way I like to approach this is by thinking about, not about how to do any of these things in the cloud, but what are the basic cloud concepts, that the things that are not going to change that support large-scale imaging, and how do you work with those? How do you change your workflows to make best use of those features in order to ready your workloads for a cloud-optimized future? One of the first things that is really different about cloud computing than on-premise computing infrastructure is that cloud is mostly a pay-as-you-go type of model. I say mostly because there are ways, in fact, to reserve computers for periods of time, and those models often end up being very similar to what you might see in something like a condo cluster on-premise computing model. But in general, the idea is that you rent, in quotes, computers and storage, and you pay for them for only what you use. So as you're using the computer and it's on, you pay for it. When you turn it off, you don't. Storage, you pay for only that amount of data that you store. And there are some options for pricing which are pretty interesting and common across multiple providers, where the cloud providers provide steep discounts on the extra capacity that they have. So when computers, this means basically that when computers are not being used, you can get them at a substantial discount, with the caveat that they could be reclaimed, maybe after some fixed period of time, maybe after some arbitrary amount of time. But this gives you the ability to get very discounted pricing for applications that can be stopped and restarted without loss of compute data, loss of the data that you're working on. So if you have a fault-tolerant type of application, you can take advantage of those pricing models. What this gives you, in summary, for compute is that you have nearly infinite capacity. I think that this is really interesting because this makes thinking about applications that use basically brute force algorithms as suddenly being tractable. Because if you can do one thing, you can do 10,000 of the same things at the same time and scale out in that way to accomplish quite a lot of work. So for permutation testing, for example, this is amazing. Another thing that is usually very helpful is that you can save quite a lot of money over buying the equivalent amount of hardware for bursty workloads. So since you're only analyzing data when you get it, and you're rate limited by, say, a scanner, for example, there's only a certain number of times you can reanalyze each subject. And often this ends up being a lot less than buying enough computing to get this done in a reasonable period of time. The drawback, though, is that since it is pay-as-you-go, this doesn't fit very well to a research environment. In say, an e-commerce environment where you have a scalable web server, as you need more web servers to handle the demand that's coming in, typically that means that you're getting more orders for whatever widgets you're selling, and that means more money that's coming in to pay for that cloud usage that is scaling up. When you scale up as a researcher and you're doing hundreds of things, thousands of things at the same time, that doesn't necessarily mean that you're going to get thousands of times the amount of grant money for your results. It might just be that you get one great paper out. So this lack of a relationship, I think, is really problematic. But that's just something to be aware of in planning. Now, when we think about the types of compute that are available on the cloud, there's basically three categories I've made here. So one is virtual machines, where you have some hardware infrastructure and a host operating system, and on top of that sits a hypervisor, and on top of that sits the guest operating systems for machines that are managed for you, and you can run applications on them. So when you get a virtual machine in the cloud, this is what you're getting. You're not typically getting hardware, although that might be a possibility, but you're getting a virtual machine. Another more lightweight option are containers, where instead of having a guest operating system for each application that you want to run, you share that with the underlying operating system with a container engine on top of that. So this is a much lighter weight to run multiple individual applications that are isolated from each other in the same environment. And then as the last option, there's what's very popular is not having to worry about the underlying infrastructure at all. So serverless is a model of computing where you let the provider manage whatever lies underneath your applications. Containers may be involved in this, or they may not be. You might just write an application, for example, that runs in some environment. Or you might just run a database, for example, and it's managed for you and you don't know anything about the underlying operating system and care even less. Let me just highlight here the things that you have to worry about in each of these models. So for virtual machines, what we care about here is the guest operating system on up. For containers, assuming that you know what container engine you're using, you care about the container itself. And for serverless, you don't care about any of the things that are underneath your application, essentially. And these are different models of that you can think about using compute on the cloud. One thing that's common, though, to any of the resources where you think about that underlying computer is that you have a choice of compute. So all cloud providers will give you a variety of different instance types that you can use, and they have different characteristics with respect to memory, with respect to processor type, with respect to storage characteristics. And these range all the way from general purpose types of instances to accelerated computing instances with specialized GPUs or hardware that might be exploited by your application to make it much faster. There is a wealth of opportunities to create your perfect dream computer, and if one computer is not enough, you can create a cluster just like you would with on-premise components. But what this means is that when you put this together with the pay-as-you-go model, you are always building a computer for your application. You're not taking your application and just running it somewhere, because that will not be cost-effective invariably. You're paying for these different choices of memory, storage, processor type. So you want to effectively use something that will give you a good time and performance and cost trade-off. Let me illustrate this with ANTs, which is Advanced Normalization Tools. There's basically two ways to use the cloud to run things faster when you have this infinite scalability. First, if you have a lot of individual things to do, individual analyses that have no dependencies, for example, here, let's talk about ANTS registrations to standard space. If you have many, many subjects and you want to do this, what you can do is you can create enough compute resources to run as many brains as you want to register, do it all at the same time, and that will cost exactly the same as if you did them one after the other on a single computer. You'll just get it done that much faster. Another thing you can look at specifically with ANTS here is that if you have multiple computing units here, tasks or virtual CPUs, you can split up the work for a single registration across those and speed things up. The problem with this is that this type of parallelism, this individual parallelism, it typically never gives you a speed up that's proportional to the amount of resources you throw at it. Now, the cost of the computer is always going to be proportional to the number of resources. So if you have 4 threads, that's going to be half as expensive as 8 threads. But the performance may not be double. So here we can see the actual numbers from some timings that I took. And you can see here that after you get to 8 virtual CPUs, there's a kind of a flattening of the curve. So you certainly don't get at 16 vCPUs half the performance that you had at 8. Things level off. And this tells you that when selecting a machine to be used for an application that can parallelize, you want to try to find a sweet spot at this knee of the curve to allow yourself to go as fast as reasonable for a single subject without additionally throwing money at it, not getting anything back or getting little back by comparison. That's a judgment call, but the principles are there. And we can see here another popular application is FMRIPrep, and this is data taken from their website. If we look just at the left-hand diagram of compute time, we can see the number of available CPUs plotted against time. The blue curve is just one subject using all the threads, and there's a similar leveling off that at 8 CPUs, you get a bigger reduction. It's less so at 16. And you can take this together with, they've looked at multiple subjects and seeing how combinations of multiple subjects and threads performs as well to find that sweet spot of how many subjects you run on how many threads to get the best kind of performance. Now, I mentioned containers besides virtual machines, and this is another layer of things to think about. Containers are a very important tool in using cloud effectively. And in neuroimaging, this has largely been motivated by a proliferation of software packages that are often difficult to coexist in a single computing environment. So if we compare something like scientific computing 30 years from now, before now, to what it's like today, we can think about the good old days where there used to be just shell and maybe some codes that were written in C or Fortran. You would stitch them together with make, and everything that you needed to give to somebody to allow them to compile and run your package could be put in a tarball and given to them, and they could compile it on their local computer, and it would run exactly the same. But now there's quite a lot of options, and these are just a few. I've probably missed many of your favorites, but we can think about a large variety of packages and platforms that need to be stitched together in order to create a scientific environment of today. And to do this in a coherent way on different types of computers often takes a lot more skill than your average researcher might have. And so a good way to think about approaching this from a neuroimaging perspective has been, instead of using a heavyweight virtual machine, use a lightweight container and put everything together in one container. However, containers from a cloud perspective are very different and have a rather different sort of function to them. So yes, containers from a cloud perspective are great for packaging services. They're also awesome because you can use them to track and manage the versions of all of the software that you add. That's also good for neuroimaging and for the use case I just described. You can specify your underlying resource needs. So if your creating a container, you can specify that it needs this many vCPUs, it needs this much memory, and then you can run that efficiently on an environment which will give you just that and no more, so you don't need to pay for extra stuff. What this enables, and what is very important in a business context, is the ability to run each container as efficiently and as inexpensively as possible, so that you can create an application that uses these containers and swaps things out as needed to improve the services, but always does so saving as much money as efficiently as possible. Now let's think about this in relationship to a common scientific workflow. And this is what I think of sort of workflow pipelines in a nutshell, what they sort of look like. So a workflow boils down to some sequence of tools that will convert the data that you have in their own special way. And each step of a workflow, just very, very generally, takes files as inputs and generates files as outputs. And those outputs are then used as inputs for downstream steps. So each of these tools in the workflow is probably unique. Some might be written in C, some might be written in Java, some might be Python, some might be Fortran, you name it. Whatever you put together in a workflow, whether it's from a single package or from multiple packages, will probably look something like this. And what these lines here describe between the tools is that there are dependencies. So showing here the different types of applications that are run here. There are files in, files out, and dependencies between, say here, tool 1 and tool A. One thing that's pretty important here is that some of these tools may have different resource needs than others. So tool B and tool A might be resource bound. They might need, by CPUs, they might need more CPUs, and tools 3 and tool 4 might need more memory. So all of these steps are different. And they may take different amounts of time. So let's think about how to run a workflow that contains multiple programs of this type. One way to do it is, as shown here, you take the entire workflow and you create a machine that is a single machine that has enough resources in every dimension that you need, memory, compute, storage, to run each phase of this workflow, and your Mongo machine will do it all. And the other option, which is really, I think, what containers were developed for, is instead to break this up. So that what you do is you create a machine, because you can do that, for each of the individual steps in the workflow to run on a machine that fits it perfectly. So here what we have is the same workflow, but we're taking each of these tools and we've created a machine that is uniquely designed for that step and running these across those. Now let's talk about storage, because we talked a lot about compute, but not at all about storage actually yet. So storage is a very important thing as well to scaling out neuroimaging. And again, here you have options, but the options tend to fall mostly along what they're good for, rather than the combinations of characteristics here. So typically you have 3 types of large-scale classes of storage. So block storage here is just like it's a disk drive, essentially. And block storage is typically what is connected to your virtual machine, and it provides that working storage that you use to access your files. You can also use block storage to create a database, for example. So it's good for anything where you would use a disk drive. File storage is sort of the next step up, and file storage can be provided by cloud providers And what it presents is a file system interface, which is just a little higher level than the block storage interface. So this is where you find sort of high performance file systems or shareable file systems across machines. And I won't talk too much about file storage because that can vary quite a lot. But the next class that is probably more important is object storage. And this is a very good class of storage for storing data, just in general. And it has very high durability, typically much lower cost than block storage. Typically it has features for archiving, for versioning, for logging. So it can be like your backup and your version control of files, your storage safety, and your audit trail all in one effectively. And if you are really advanced, what you can do is think about taking pools of data from multiple sources, and you can even put that all together sometimes to actually query what you have using database types of methodologies. But again, I won't talk too much about that. It's a very powerful metaphor for how to move forward with storing data. So object storage is where you would put kind of your master copies of all of your neuroimaging data, all of the types of results that you want to keep. And block storage on the other side is where you would keep your working data. So you end up with the basic processing pattern for cloud that looks something like this, where you have your data and that is stored on some object storage after you've gotten it from the scanner. You have some tool or tools that take compute of some sort plus storage, and then you process, you run each tool, you take the outputs of that, and then you store them back onto object storage. And this is what basically workflow looks like in the cloud. There's this copy phase, there's this compute phase where you have specialized compute. And I'm just going to say a few words about security and collaboration, just writ large. So because cloud computing is a global platform, collaboration is really very easy. Researchers have the ability to compute at the location where the data are. So you can imagine having a platform where you have shared data and you create compute resources exactly where it is. So there's no issue of ever taking it out of the institution. You are using it exactly where it should be. You have access to it as a collaborator, and you don't have to risk losing it or having unauthorized sharing. Essentially, you can keep track of everything. Part of this also is because you can program compute. I think because you can program the computing infrastructure on cloud computing, it's much easier to create a secure environment where you're making sure you have appropriate authentication, appropriate audit trails, and appropriate access controls than it is to do so, I think, in similar on-premise environments. So without saying a lot about this, this is something that typically you want someone to manage for you, but are very easy to do on cloud platforms. So I think that this is one of the driving forces, perhaps, in movement of large-scale workflows, neuroimaging, to the cloud, even beyond the performance and the benefits, the obvious benefits to research, is that taking care of the data is probably easier on such platforms. So with that said, this is kind of my big picture image of what a generic cloud-based neuroimaging environment looks like. So you have some aspects of specialized computing infrastructure that you may create for a specific use case, a specific application. Here I chose FreeSurfer as a compute-intensive application where you might want to run many subjects all at once, and you might want to create a cluster just for that purpose, and then 2 days later, shut it down and look at the results. Similarly, you might want to create a specialized GPU cluster to do some machine learning algorithm, to run some machine learning algorithm that you've developed. And that may be something that requires different cluster, different hardware. So you don't need to try to figure out where to get this from, you just make it. There's a lot of need for specific applications on computers. So maybe you need a Jupyter notebook with a big amount of memory, or an RStudio instance to do some post-analysis. Maybe you need a productivity tool, not shown here, for example, like a Windows desktop. And this would be what that would look like. And you would save your data, of course, on object storage, and then share those data sets with other labs who may come to your site to then create new environments of their own. So with that in mind, let's talk about how to take advantage of this these features for writing workflows that are computationally efficient in the cloud. These are some traditional approaches that people have taken. And I want to talk about these because they're not necessarily bad, they just don't take advantage of the features that will really allow you to scale in cloud computing. So let's take as the basic entry point, writing workflows in Bash or your favorite scripting language. The pros of that are that it is a linear approach. You have one step after the other. This is easier than writing workflows where you express complex dependencies and parallelism. And it's reproducible. At least you know what you've run and what steps have been executed. The cons of this are that parallelization is difficult, although there are ways to do it. They're tricky and often not very portable across different architectures. And worse than that, rerunning specific parts of a script usually aren't automatic. It ends up being sort of stage 1, stage 2, stage 3. You're commenting out bits to rerun things that have to be done, or changing subject numbers or something like that. And it can be kind of a mess to do that in a general way. And this is why really specific languages to describe workflows were created. So the oldest of those that I know of is Make, and the pros of GNU Make, and I've written about this in the past as a fine way to get a step up above Bash, is that 45 years of experience in a programming model means that there's no bugs. The cons of Make is that the syntax is a bit arcane. It can be difficult for expressing dependencies with complex inputs and outputs, and that would be pretty much every neuroimaging application ever written. So explaining that you really need all of these outputs to be here, and there's 25 outputs, can be sort of tricky with Make. A third option, which is the most modern of these, is NiPipe, and many people use this, and this is the foundation of FMRIPrep. And the pros of this are that it is all in Python, so you only have to learn the one language to describe how to write a full workflow. But the cons of this, as I'm going to describe, are all Python. So what I mean by that is that if you are making a monolithic pipeline where you have one application to rule them all, then necessarily you have to create a machine to run that will be big enough to accommodate the largest of all of the demands of all of the parts of the container that you need. So NiPipe is not necessarily that great at taking advantage of different stages of an application, which may have different resource demands, and that's similar to Make and certainly Bash as well. Let's talk about what we need in terms of future-proofing neuroimaging workloads. Those workflow languages aren't quite going to cut it in many ways, but we do need to stick to certain principles. So these are, after much thinking and much reducing the numbers of thoughts that I've had and the recommendations that I've had, I can bring it down to these three. So the first is, when writing a neuroimaging workflow, stick to the greatest hits. By that, I mean stick to running workflows that will run on the laptop that you have in front of you, the compute cluster that is in your university's data center, and any cloud provider that gets thrown at you. So that means not using very specific and novel and exciting services that are provided, maybe serverless computing options provided by any cloud provider, because they're probably not going to be anywhere near as portable, and you never know what is going to be thrown at you as a resource that you need to use in your next postdoc or faculty gig. So that is, I think, one of the most important things, is to be able to run across multiple platforms. The next thing, of course, is don't just write a bash script, but express your code express your neuroimaging needs as a workflow, with consideration to being able to break out each step, especially those with radically different resource demands, so that they can be run on specialized hardware. This is not something that I think that most people think about when currently writing workflows for the computer in front of them or the HPC in their university center. But it's something that is going to become increasingly important, if only because that's how you save money on running things on the cloud, running things actually anywhere. When you have more selection of resources, then it's going to be important to select only those things that you need. And that's using a workflow, I think, is a very elegant way to do it without having to become an expert in some individual cloud platform and how they would like you to orchestrate different steps. If there's a layer of abstraction in between the cloud provider and what you're writing that will run on anything, that's awesome. And the final thing is really important, and it's about managing your data. Because of this need to copy data from wherever it may be on object storage to the computer that you're running on, and the need to copy it back, and also the fact that the storage of the data on both object storage and your local storage drives is going to incur a cost. Don't just save everything. Don't just think about what you're writing, what you're saving, what you're needing, and do that from the very beginning. So that means a lot about thinking about good naming conventions, good directory conventions, doing things that work well with cloud systems, which might allow you rules for automatically archiving files or automatically deleting them, whatever you might want to think about doing, implement a plan for that. And these will be ways, these are good practices anyway. These are good practices no matter what you're running on, but these also make your neuroimaging applications future-proof and scalable no matter what cloud platform you're looking at. So I'm going to give a concrete example here of a way that you can implement these characteristics using a software package called Nextflow to write your workflow. And I like Nextflow because I think that it makes it very easy to do all of these steps. They're almost automatic and almost free for using this software to write your workflows. And if I were starting a neuroimaging lab today, this is what I would teach and use. So what Nextflow is a specific language for writing workflows. It comes from genomics, and as such is meant to handle a lot of the things that are tricky about neuroimaging applications as well. So, for example, I mentioned that Make is pretty bad at allowing you to specify very complex rules for dependencies with multiple input and output file structures. And that's every genomics application ever written too. So Nextflow is really, really good at allowing you to specify what the inputs are, the outputs are, and have rather complex ways of deciding whether conditions are met or not. Another feature of Nextflow that is really important is that it is just a matter of configuration file to move from your laptop to a cluster, or to move from a cluster to cloud cluster, or to move to from a cloud cluster to a cloud native containerized type of system, which might be sort of a cross between serverless and containerized type of service that really allows you to optimize your performance for each step of your application. So it's got native support for object storage as inputs and for containers as workflow steps. And what I'm going to do here is just show you some of these features, and there is a more complete example in the notes that go along with this class that you can try it yourself on the data set that we're using and see how it goes for you on your laptop. But just to give you some ideas about the features here and what this looks like, the way that Nextflow works is that you have processes. And here I'm hoping that people are mostly familiar with skull stripping, and this is using BET from the FSL package. You say how many CPUs you need and what your task name is. You specify your input files, and then you specify your output files. And at the end here, you have a little script, which can be bash commands, or it can be any scripting language you like. So you can mix and match as you wish, keeping it as simple. You know, if you get some recipe from someone in some other language that works, just use it. The basic idea is that you create channels with outputs and inputs and pass them along to each other. So here, if we extend this BET recipe here to have a second process, what it can do is it will take from the output, which was next process data, the next thing that it will do, it will take that as an input, and then you can write whatever recipe you like to process that. And so the order of these processes, as with most workflow languages, doesn't matter at all, except to make things logical for you. But you specify inputs and outputs and connect them to each other. And this is the way that the workflow language knows what the dependencies are. Now, that's pretty basic for a workflow language. But here are some neat features that help you to really take advantage of cloud computing. So here, for example, in this Nextflow example, we have the ability to show we're taking a channel, and this is from the notes for the class for this course. We're taking one files directly from S3, and so for two subjects, we're taking their anatomical T1 weighted images. What this will do is it will, if set up appropriately so that you have the credentials to access the files on S3. In this case, they are open, but you still need to specify that you don't need to actually authenticate, so you don't have to have an AWS account to get to them. It will check to see on your local computer whether those files have been staged, and if they need to be copied, we'll copy them across. This is another really great example here. Each of these steps does not need to just be a script. It can be a container, and you can mix and match containers, and you can mix and match, and you can have scripts and containers side by side. So you do not need to make the jump to containerizing your entire workflow all at once. You can do stages, and each step is a single container. Here I've got that the parcellation here is going to use a FreeSurfer container. This could be just a part of FreeSurfer. It could be all of FreeSurfer. This here is the BIDS FreeSurfer container. You can use Singularity, Docker, but you can specify how many CPUs you need and how much memory you need. So this gives you the ability to break up a workflow, as I described, into multiple steps, where each step that has different resource needs can run on a little computer created just for it and do so very effectively. To take advantage of that, what you would need to do then is you would have to have each of the containers, each of your steps in the workflow be a container, so that you could specify to use a containerized service on one of the cloud providers. and it would be able to take advantage of these resources and run things for you more efficiently. And that's how you would do that. But if you just had a cluster, for example, you could mix and match, and it wouldn't matter. And like I said, the cluster could be on-premise or it could be a cloud cluster. It really doesn't matter. You have many options for how to do this, and I think that flexibility is really important. It has nothing to do with the scalability, but it's important. And that is, and with that, I will end. Thank you very much, and I can be reached at this email address if you have any questions.